worry about that stuff as much. The sentence, a function of the form of the velocity. Just get that stuff in the middle. Are we good, or do we need another minute? So everything, well, almost everything on this equation, on this function, should look very familiar because we've talked about all these parts several times. There's just one little difference. So our y value or our ending value here is still the final amount that we end up with. Okay, whether we're talking about, yesterday we talked about like an increase like with movie tickets or like carnival tickets or something like that. And they said, hey, the carnival is increasing by 10% every year. What's it going to be 10 years down the road? Well, they could also say movie tickets, right? Movie business is kind of really going downhill. Movie tickets for a theater are decreasing by 6% every year. How many people are going to be going to the movies in 10 years or something like that? So everything has to do with being decreasing, and y still represents our final amount. A is still our initial amount, that starting value, whether we're talking about money, how much money you put in the bank to start out, or how many people are going to the movies this year. It's still our initial amount. In the parentheses is where things start to change, right? Instead of doing 1 plus something, we're doing 1 minus our rate of decay. And again, it's in decimal form. Converting from percents to decimals tripped a couple people up yesterday, so we'll get a little bit more practice at that today. And lastly, it's to the t. So we're still dealing with time, like we have been for the last week or so. So if we look at these tables, and this is a lot what we did in the warm-up, but if we look at these tables, which one of those tables is exponential growth? We talked about yesterday. Which one of those is exponential growth? B is, right? Because we're multiplying by 2. A number that's bigger than 1, so that means that what's going on has to be growing. So that would mean that A is decay, right? Since we're multiplying by something that is less than 1. If we were to put this first, if we were to put part A into our formula and write an equation for it, we'd say y equals our initial amount, 270 times 1 minus 1/3. Remember, 1/3 is our rate of decay, and then just to the t, or however much time we want to be talking about. So writing the equation is just like what we've been doing this whole time. Put a rate of either growth or decay in that spot for r, and simplify. So there's a couple problems I'm going to need to see done before you get your worksheet for today. This is one of them. Go ahead and decide if we were looking at exponential growth with these tables, decay, or neither. Exponential growth, decay, or neither. This is just like what we were doing in the warm-up, except they put the numbers in a table form instead of a list. A lot of people got the first one. Almost, I think everyone I've seen has nailed the first one. Be careful on the second one.
Oh, then it must be me.
And remember, it has to be exponential. Give you about 30 more seconds. Okay. I will check those when you come up to get your worksheet. So, the function P equals, all of that represents the population of a town after T years. What percent does the population decrease each year? So, this is a classic, I mean, you can see I screenshotted it right from one of the worksheets. This is a classic question that we will see going through today. Remember, in this parentheses, we're trying to figure out what percent does the population decrease each year. The population does not decrease 94% every year. What we need to do, just like we did yesterday, remember how we set this up yesterday, except we have 1 plus r? Do we remember doing that? A little bit. And we were just really what we ended up doing is if they gave us like 1.16, we knew that the increase was 16%, right? We could see that really quickly. We're going to see that same idea with decay. What we end up finding, this is the official setup that we have. But what we end up finding is that our rate is 0.06. So it's whatever our decimal is at inside that parentheses, the difference between that decimal and 1. So as a percent, it would just be 6%. Do we see that, or did I skate over that too quick? Yeah, Michael?
Where do you get the 6 from?
So, what?
Yeah, I was agreeing with that.
Yeah. So if we were to actually solve this top one, right, we would subtract 1 from both sides. So we would have negative r equals negative 0.06. If we do 0.94 minus 1, 0.94 minus 1, we go to 0.06. Now we have a negative on both sides, so they just cancel each other out. So our r would be 0.06. It's the difference between that decimal and 1. Does that answer it, Corbin?
Yeah.
Okay. Michael, does that help?
That's a bit.
That's it. If we, here, I'll give you another example. If inside those parentheses we had 0.8 to the t, then our rate would be 0.2. So it's the difference between that decimal and 1 is our rate. If inside those parentheses we had 0.75, our rate would be 0.25. Are we following a little bit? Okay, we'll get some more practice. Right now we'll get some more practice on it. But what percent, so the function a equals, we have the scary fraction in the middle, but we can figure it out. It represents the area of coral reef, blah, blah, blah. What percent does the area of the coral reef decrease each year? What? It's not 9. It's not 90. But go ahead, do this on your own. You see this before you get the worksheet as well. Really what we need to end up doing is 1 minus, we'll get our rate. People,
Yeah.
if we have 9/10, and we want to find the difference between 9/10 and 1, if this whole thing is 1, how many tenths are left over? 1/10. Hopefully that's something we can do in our head. 1 minus 9/10. See, a lot of people type in our calculator. A little bit of number sense needs to go through our brain. So 1/10. If we were writing that as a percent, well, I'll let you write that as a percent. So another example of the type of problem we'll see. The value of a car is $21,500. It loses 12% of its value each year. Write a function that represents the value of the car after t years. So we're going to write our equation. Our starting value is 21.5. In our parentheses, to talk about our decay, I guess I didn't write it up here. Our rate of decay, there we go. Yeah. In our parentheses, to talk about our decay factor, we have 1 minus our rate of decay, which is 12%, so 0.12. Let's do the t. Now to simplify it, 115. So that is how we would write our function. Just like what we were doing yesterday, except in our parentheses, we're going to have something that is less than 1. Now, if I said find the value of the car after 7 years, how would you find that? We put 7 in for t, right? T, remember, represents our time. So we just would plug 7 in for t, we could find the value of that car after 7 years. Last practice problem, and you can get your homework sheet. The car loses, another car problem. 9% of its value each year. Does it tell us how much the car? Oh, oops, it's the same car. So you buy it for $21,500. But this time it loses 9% of its value each year. So you need to write a function and then find the value of the car after 12 years. I need to see those 3 practice problems that I showed done. Yeah, so any of them that, I'll put them all on the same screen, so give me just a second. But any of those 3 that said practice at the top, I need to see those